In one of my last videos, I have told you how you can use the Gram-Schmidt orthogonalization process to find an orthonormal basis of an Euclidean vector space. You may ask yourself now, why do I need an orthonormal basis of my vector space? Well, in this video I will tell you a few things you can do with an orthonormal basis. We will talk about the Fourier-representation of vectors. But first of all, I want to remind you what an orthonormal basis is. Let V be an Euclidean vector space. So an Euclidean vector space is a vector space V over the field of the real numbers R together with a scalar product. That scalar product is denoted like that. A scalar product is a positive definite symmetric bilinear form. Let B is equal to B1 to Bn be a basis of that vector space V. Then the basis B is called orthogonal basis of V if the scalar product of Bi with Bj is equal to 0, for I is not equal to j. The basis B is called orthonormal basis of V if the scalar product of Bi with Bj is equal to 0, for I is not equal to j, and the scalar product of each vector Bi in the basis B with itself is equal to 1. That here means that the Euclidean norm of each vector Bi in the basis B is equal to 1. The Euclidean norm of a vector x in the space V is given by the square root of the scalar product of x with itself. It's denoted like that. So this here is the Euclidean norm of a vector x in the space V. Let's take a look at the Fourier representation of a vector in an Euclidean vector space now. Let V be an Euclidean vector space with an orthonormal basis B is equal to B1 to Bn. So that basis B is an orthonormal basis. Let square bracket x B is equal to x1 to xn be the coordinate vector of an vector x in the space V with respect to that orthonormal basis B. Then these real numbers here, x1 to xn, so these real numbers xk, for k is equal to 1 to n, are called Fourier-Coefficients of the vector x with respect to the orthonormal basis B. If you have already watched my video about coordinates, you may know that it can be a little bit of work sometimes to find the coordinate representation of a vector x with respect to some basis. For example, it could happen that you have to solve a linear equation system. But in the case of an Euclidean vector space together with an orthonormal basis, it is extremely easy to find the coordinates x1 to xn with respect to B. Because there is a calculation formula for these xk. Let's take a look at the following result. Let V be an Euclidean vector space with an orthonormal basis B is equal to b1 to bn. Let x be a vector in that vector space that has the Fourier coefficients x1 to xn with respect to that orthonormal basis b. Then you can calculate these coefficients x1 to xn the following way. So xk is equal to the scalar product of x with bk, for k is equal to 1 to n. You see, it is pretty easy to find these unique coefficients x1 to xn here. To find the kth coordinate of x, you just have to calculate the scalar product of x with the kth vector bk in the basis b. That here also means that you can represent x the following way by using the orthonormal basis b. X is equal to the sum from k is equal to 1 to n of the scalar product of x with bk times bk. This representation is unique. That here, the scalar product of x with bk are the unique coordinates of x with respect to the orthonormal basis b. You also have this result here. If you have another vector y in the space V with Fourier coefficients y1 to yn, then the scalar product of the vector x with the vector y is equal to the sum from k is equal to 1 to n of xk times yk. This sum here is the standard scalar product of the coordinate vector of x with respect to p and the coordinate vector of y with respect to b in Rn. You can denote the standard scalar product in Rn by using a dot. So you get this here in the end. That result is helpful if you want to calculate scalar products by only using the coordinates of vectors. Also keep in mind that this here on the left can be some really difficult and abstract scalar product in a general Euclidean vector space, but this here on the right is always the easy standard scalar product in Rn. Let's take a look at an example now. Let V be R2 with the standard scalar product in R2. That means the scalar product of x and y is equal to the first entry of x times the first entry of y plus the second entry of x times the second entry of y. That here is the standard scalar product in R2. In one of my last videos, we used the Gram-Schmidt orthogonalization process on that basis C here and got the following orthonormal basis b bar. So b bar is equal to that here, and this here is the vector b1 and that here is the vector b2. So this here is an orthonormal basis of R2, and we calculated it by using the orthonormalization process on that basis C here. We want to find the Fourier coefficients of the vector x is equal to 1 and 0. So the coordinates x1 and x2 with respect to the orthonormal basis B bar. Because B bar is an orthonormal basis, we will use our calculation formula to find x1 and x2. So by using that formula here, we get that x1 is equal to the scalar product of x with b1. So that here is x and this here is b1. So we plug b1 and x in the scalar product here. So we get that this here is equal to 1 divided by the square root of 2 times the scalar product of the vector x, which is 1, 0, with that vector here, 1, 1. So now this here is equal to 1 divided by the square root of 2 times 1 times 1 plus 0 times 1, which is 1 plus 0. So in the end, this here is equal to 1 divided by the square root of 2. So the first coordinate x1 is equal to 1 divided by the square root of 2. By using that formula here again, we get that x2 is equal to the scalar product of x with b2. So that here is x and this here is b2. So when we plug these vectors in the scalar product, we get the following: 1 divided by the square root of 2 times the scalar product of the vector x, which is 1, 0, with that vector here, 1 and minus 1. So this is equal to 1 divided by the square root of 2 times 1 times 1 plus 0 times minus 1, which is 1 plus 0, and in the end we get 1 divided by the square root of 2. So the second coordinate of x with respect to the orthonormal basis b bar is equal to 1 divided by the square root of 2. So we have found the coordinates of x with respect to the orthonormal basis b. We can check if that solution is true. So x1 times b1 plus x2 times b2 is equal to 1 divided by the square root of 2, which is x1, times 1 divided by the square root of 2 times the vector 1, 1, which is the vector b1, plus 1 divided by the square root of 2, which is x2, times 1 divided by the square root of 2 times the vector 1 and minus 1, which is b2. This is equal to 1/2 times the vector 1, 1 plus 1 minus 1. This here is equal to the vector 1 and 0, and that vector 1 and 0 is the vector x. So you see, these two numbers, x1 and x2, are really the coordinates of x with respect to that orthonormal basis b bar here. Let's take a look at something more difficult. Let P2 be the vector space of all polynomials of degree smaller or equal 2, together with the following scalar product. So the scalar product of a polynomial p with a polynomial q is equal to the integral from 0 to 1 of p times q. So normally we would now have to check if this here is really a scalar product, but we won't think too much about it, because the example already tells us that it is a scalar product, so we will just believe it. Now we have given the following basis C of P2. C contains the polynomials 1, x and x squared. And now we use the Gram-Schmidt orthonormalization process on C to get an orthonormal basis B bar. So this here is B1, that here is B2, and that here is B3. You can try to calculate that orthonormal basis B bar yourself as an exercise. You just have to use the orthonormalization process on the basis C. Now we have the following polynomial P. P is equal to x plus 1. We want to find the Fourier-coefficients x1, x2 and x3 of P with respect to that orthonormal basis here, B bar. We can use our formula to find x1, x2 and x3. So x1 is equal to the scalar product of P with B1, and this is equal to the integral from 0 to 1 of x plus 1 times 1 dx. So this here x plus 1 is P, and that here 1 is B1. When we solve this, we get 3/2. So the first coordinate is 3/2. I have used a program to calculate that integral here, but you can also solve it by hand if you want. Now x2 is equal to the scalar product of P with B2, and we get that integral here. So this here x plus 1 is P, and that here 2x minus 1 times the square root of 3 is B2. When we solve this, we get the following result: the square root of 3 divided by 6. So the second coordinate is equal to the square root of 3 divided by 6. I have used a program again to solve that integral here. Now x3 is equal to the scalar product of P with B3, and this is equal to that integral here. So this here x plus 1 is P again, and that here 6x squared minus 6x plus 1 times the square root of 5 is B3. When we solve this integral, we get 0 in the end. So the third coordinate x3 is equal to 0. I have used a program again to solve that integral here, but you can solve it by hand if you want. These are now the coordinates x1, x2 and x3 we were looking for. We can check directly if our solution is true. So x1 times b1 plus x2 times b2 plus x3 times b3 is equal to 3/2 times 1. So this here is x1 and that here 1 is b1, plus the square root of 3 divided by 6, so this value is x2, times the square root of 3 times 2x minus 1, which is b2, plus 0 times b3, so 0 is the third coordinate, and b3 is that here, but it's a multiplication with 0, so we don't need to write it down. So and this is equal to 3/2 plus 1/2 times 2x minus 1, and that is equal to 3/2 plus x minus 1/2, and in the end we get x plus 1, which is the polynomial P. So these three numbers here, x1, x2 and x3, are really the coordinates of the polynomial p with respect to the orthonormal basis b bar. Okay, I hope you are now able to calculate the Fourier coefficients of a given vector x of an Euclidean vector space with respect to an orthonormal basis b. If you liked this video, please consider subscribing to my channel. It would help and motivate me to keep creating videos.